In the last lecture, we introduced the notion of an orthonormal basis and we looked at the expansion in terms of an orthonormal basis. We found that if we start with R k and we have any orthonormal basis phi 1, phi 2, phi k, an orthonormal basis for R k, then we have the following result. 1, any vector x in R k has this expansion x comma phi j, where you recall this x comma phi j denotes the inner product, which is the same as phi j transpose x, and this is true for every x in R k, and this is called the Fourier expansion of x with respect to the orthonormal basis B. Then we found that the inner product x comma y is summation j equal to 1 to k x comma phi j y comma phi j for every x y in R k, and this was called the Plancherel's formula. Then we had for the length the identity that norm x squared, which is x comma x, which we put y equal to x above, we get j equal to 1 to k x phi j squared for every x in R k. Now, let us look at an example to illustrate all these facts. Let us take R 3 and let us take B to be the basis phi 1, phi 2, phi 3, where phi 1 is the vector 1 by square root of 2 into 1 1 0, phi 2 is the vector 1 by square root of 2 into 1 minus 1 0, and phi 3 is the vector 0 0 1. We have seen that this is an orthonormal basis for B. So, this is orthonormal basis for R 3. So, let us look at these Fourier expansions and Plancherel's formula and the Parseval's identity. Now, we have take any vector x equal to x 1, x 2, x 3 in R k. So, look at any vector x in R k, we have x phi 1, which is the dot product of x with phi 1, which is 1 by root 2 into x 1 plus x 2, and since the third factor coefficient here is 0, there is no contribution. Similarly, x phi 2 is 1 by square root of 2 into x 1 minus x 2, and x phi 3 is x 3. So, we have these three Fourier coefficients, hence x must be equal to x phi 1 phi 1 plus x phi 2 phi 2 plus x phi 3 phi 3. Let us check whether this is true. The right hand side is x phi 1, which is 1 by square root of 2 into x 1 plus x 2, which we obtained here, plus into phi 1. Phi 1 was 1 by square root of 2 into 1 1 0, plus x phi 2, which we have here. If we substitute that, we get 1 by root 2 into x 1 minus x 2 into phi 2 is 1 by root 2 into 1 minus 1 0, plus x 3, x phi 3 is x 3 times phi 3, which is 0 0 1. If we now simplify this, this is nothing but x 1 plus x 2 by 2 plus x 1 minus x 2 by 2, if you look at the first components all along, and then x 1 plus x 2 by 2 minus x 1 minus x 2 by 2 and x 3, which is exactly equal to x 1, x 2, x 3, which is x the left hand side. So, this verifies the Fourier expansion for this vector. So, the Fourier expansion of x with respect to b is therefore, x is equal to x comma phi 1, which is 1 by root 2 into x 1 plus x 2 into phi 1 plus 1 by root 2 into x 1 minus x 2 into phi 2 plus x 3 into phi 3. So, this verifies the Fourier expansion. Now, let us look at a vector x and a vector y, then x phi 1 is 1 by root 2 into x 1 plus x 2 as we found above, x phi 2 is 1 by root 2 into x 1 minus x 2 and x phi 3 is x 3. This is what we found. Similarly, we have y phi 1 is 1 by root 2 into y 1 plus y 2, y phi 2 is 1 by root 2 into y 1 minus y 2 and y phi 3 is y 3. So, if we take the product of the corresponding Fourier coefficients, we get x phi 1 into y phi 1 plus x phi 2 into y phi 2 plus x phi 3 into y phi 3, which is equal to x phi 1 is 1 by root 2 into x 1 plus x 2 into y phi 1 is 1 by root 2 into y 1 minus y 2 plus x phi 2 is 1 by root 2 y 1 plus y 2, x 1 minus x 2 into 1 by root 2 into y 1 minus y 2 plus x 3 y 3. Now, if we simplify this, this is nothing but x 1 plus y x 1 y 1 plus x 2 y 2 plus x 3 y 3, which was the inner product of x and y. So, verifying the Plancherel's formula. What does the Plancherel formula say? That the product of the corresponding Fourier coefficients, one, the product of the second Fourier coefficient, the product of third Fourier coefficients, when they are all added up, we must get the inner product, and that is what we get here. And finally, we have x phi 1 squared plus x phi 2 squared plus x phi 3 squared is equal to x phi 1 was 1 by root 2 into x 1 plus x 2. So, this is x 1 plus x 2 squared plus 1 by 2 into x 1 minus x 2 squared plus x 3 squared. And if you simplify this, this is just x 1 squared plus x 2 squared plus x 3 squared, which is the length of x squared. So, this verifies the fact the sum of the squares of the Fourier coefficients, the sum of the square of the first one, square of the second one, the square of the third one. If we add the sum of the squares of the Fourier coefficients, we get the length squares, and that is verifying the Poisson's formula. I am sorry, this is called the Parseval's identity, verifying Parseval's identity. So, thus we have the expansion in terms of an orthonormal basis, giving rise to easy ways of computing the inner product, the norm in terms of the Fourier coefficients, as we would have done normally with the standard ordered orthonormal basis. Then at the end of the last lecture, we raised the following question. Supposing I have R k and I have S, a linearly independent set in R k, then either S is a basis for R k, and when can this happen? That is when, let us say S is the set U 1 or phi 1, phi 2, phi r. This will happen when R equal to k, or S can be extended to a basis for R. We have seen this before, that any linearly independent set, if it is not a basis, then we can append k minus r vectors to it to get a basis. Now, suppose if it is a basis, then it is already an linearly independent set and we have no problem. If it is not, we have to append k minus r. Now, suppose we start with S an orthonormal set, say S is phi 1, phi 2, phi k, phi r. Then again, because S is orthonormal, that says S is linearly independent. Now, if S is linearly independent, as we observed before, either S is a basis, that is if R equal to k, but if it is a basis and since it is already an orthonormal set, therefore, S is an orthonormal base. If it were not a basis, S can be extended to a basis. The question arises, the extended basis may not be orthonormal, and therefore, we ask, can we extend S to an orthonormal basis? So, can we extend S to an orthonormal basis for R k? Whenever I said basis, I always meant R k, for R k. Now, we shall investigate this question, and as I mentioned, the main technique involved in this is what is known as the Gram-Schmidt orthonormalization. Before we describe this procedure, let us say what does this Gram-Schmidt do? Okay. What is the goal of this process? The goal of this process is the following: we are given you are a linearly independent set in R k. We are given, we are start with a linearly independent set in R k. So, this is the starting ingredient. Now, what we must do something with this, then we want to produce OS. O stands for orthonormal, S stands for that you start with this set S. So, OS, which we will call as phi 1, phi 2, phi r, an orthonormal set of the same size as S. S had R vectors, we want OS also to have R vectors, but that is not a big deal. We want it to be such that we want to construct this orthonormal set in such a way that certain things happen. One, obviously, we would like that whatever subspace that S spans, OS must also span the same subspace, such that 1 LS equal to LOS. This is our main aim. Whatever subspace S spans, the OS must also span the same. What happens then? Then OS becomes an orthonormal set in S, it spans S, and therefore, it will become a basis for OS. So, this OS orthonormal set in R k. So, we would like to construct in such a way that the subspace spanned by OS is the same as the subspace spanned by S, and hence OS will become an orthonormal basis for LS. Actually, the procedure does even more. It does the following. It constructs these vectors phi 1, phi 2, phi 3, phi r in a recursive manner such that at each stage, for example, at the first stage we will construct phi 1 and phi 1 will generate the same subspace as u 1. Then at the second stage we will have got phi 2 and the phi 1 and phi 2 will generate the same subspace as u 1 and u 2. It will go on stepwise and at the end LS will be LOS. So, it does the following. L of, okay, let us denote Sj OS, okay, let us use a certain convenient notation before we state this. Let us take Sj to be u1, u2, uj. We had r vectors u1, u2, ur. Out of this we are selecting the first j vectors. So, the j has to be something between 1 and r. Then correspondingly we will construct OSJ, which is phi 1, phi 2, phi j, that is the first j vectors that we construct orthonormal, such that the space spanned by Sj is the same as the space spanned by OSJ. So, that at the end when j equal to r, Sj will become S, OSJ will become OS and LS will be equal to OSJ. So, when j equal to r, we get Sj equal to S, OSJ is equal to OS and LS equal to LOS. So, this is the goal of this Gram-Schmidt process. At each stage it produces orthonormal set which sweeps the vector space or the subspace spanned by all those vectors in the U case up to that stage. So, let us now describe the procedure. So, the GS procedure, the Gram-Schmidt, we will denote it by GS. The Gram-Schmidt orthonormalization procedure goes as follows. As we said, our aim is to eventually get an orthonormal set. So, there are two things involved. One is we have to get orthogonalization and then we have to get a normalization. The first stage is to get the orthogonalization done. So, the first stage is to get orthogonalization, and then once we get orthogonalization, the next step will be to do normalization by just dividing by the length. So, we have this set S u1, u2, ur. Our job is we now find V1, V2, Vr such that Vi comma Vj is equal to 0 if I not equal to j. That is, they are orthogonal to each other. That is what is meant by saying getting the orthogonalization, and the space spanned by u1, u2, uj, the first j vectors is the same as the space spanned by v1, v2, vj, and this is true for j equal to 1, 2 up to r. So, now we are not worried about normalization, we are only worried about orthogonalization. So, at the stage when j equal to r, when the process ends, we would have got an orthogonal basis for this V1, V2, Vr will form an orthogonal basis for Ls. The way to get this V1, V2, Vr is what we will describe now. So, we get V1, V2, Vr as follows. We first define V1 to be just u1. That is the first step. We start with the first given vector, then we find the length of u1 squared, which is V 1 comma V 1, which is the same as U 1 comma U 1. So, since V 1 is U 1 is given to us, we know V 1. The next step is to go to V 2. The V 2, we now use the U 2 information. If you look at it a bit geometrically, we have U 1 here and U 2 here. Now, the U 2 may be thought of as having two pieces of information, one which is along the direction of U 1, the other one perpendicular to that. So, the U 2 is made up of this vector and this vector, and since we already have the U 1 direction under control with our V 1, we have to only worry about producing this orthogonal direction U 2. For that, from V 1 we must subtract this projection, and that is obtained as follows. You start with U 2, from that the subtraction of this projection is given by, you take the inner product of U 2 with V 1 and divide it by V 1 square, that unit vector in that direction. Now, you see what happens. We can divide by V 1, we must be very careful that the denominator is not 0. So, the denominator is not 0 requires that V 1 is not the 0 vector. Now, V 1, if V 1 were the 0 vector, that would mean that the U 1 is the 0 vector, but U 1 cannot be 0 vector because we are assuming U 1, U 2, U r are linearly independent. So, this is perfectly well defined, and you note now if we take the inner product of V 2 and V 1, it is 0, because then that shows therefore that V 2 and V 1 are orthogonal to each other. Now, having obtained V 2, we find the length of V 2 squared. So, now we have got V 1 and V 2 are orthogonal, and we observe that anything that can be written as U in terms of U 1 and U 2 as a linear combination can also be written as a linear combination of V 1 and V 2, because U 1 can be written in terms of V 1 and U 2 can be written in terms of V 1 and V 2. So, we have V 1 V 2 can be written as a linear combination of U 1 U 2, and U 1 U 2 can be written as a linear combination of V 1 V 2. Therefore, L U 1 U 2, the space spanned by U 1 U 2 is the same as space spanned by V 1 V 2. Now, therefore, once we know V 1, we have the definition for V 2. Now, we define recursively. Suppose we have defined V 1 V 2 V j minus 1, then we define V j as follows. V j, for V 1 you started with U 1, for V 2 you started with U 2, for V j you start with U j, and then you have to subtract all the information along the projections of the previous directions. So, that is obtained by taking I equal to 1 to j minus 1, all the previous stages, take the vector U j, look at its projection along V I, the previous direction, and subtract it, then look at the unit vector in that direction. This is how V j is defined for once we know all the previous ones. Again, you know that this will not be 0 and you get the orthogonal vectors. So, the general procedure therefore is V 1 is defined as U 1 for j greater than or equal to 2, it is defined as I equal to 1 to j minus 1, uj vi by length bi squared for j greater than or equal to 2. So, once we know V1, we know V2, and once we know V1, V2, we know V1, V2, V3, and once we know V1, V2, V3, we know V4, and we go on recursively like that, and at the rth stage we get then Vi Vj is equal to 0 for I not equal to j, and the subspace spanned by u1, u2, uj is equal to the subspace spanned by b1, b2, vj, and this is true for any j between L and R, and in particular if j equal to k, j equal to R, we get the subspace spanned by this set u1, u2, ur, that is the original set given to us is the same as the subspace spanned by v1, v2. So, therefore, first we have done the orthogonalization process. We were given linearly independent vectors u1, u2, ur. Recursively step by step we have produced a sequence v1, v2, vr of vectors which are orthogonal to each other, and in such a way they sweep the same space at each stage as swept by these corresponding u's. Then the second step in the process is the normalization. We want all these vectors to be length, we let phi j to be v j divided by the length of v j. Then phi j's become then O s equal to phi 1, phi 2, phi r is the orthonormal set we are looking for. What are we looking for? We want them to be orthonormal set such that is L of u1, u2, uj is equal to L of phi 1, phi 2, phi j for 1 less than or equal to j less than or equal to r, and in particular L of s is equal to L of OS. So, OS becomes an orthonormal basis for the subspace spanned by S. This process is called the Gram-Schmidt orthonormalization process. Let us look at one or two examples. Let us take R4 and let us take S to be consisting of these 3 vectors u1, u2, u3, then where we will define u1 to be 1, 1, 1, 1, u2 to be 1 minus 1, 1 minus 1, u3 to be 1, 0 minus 1, 0. Okay. It is easy to verify, we will leave the as an exercise. It is easy to verify that S is linearly independent. Since it is a linearly independent set, now we are going to apply GS to it, the Gram-Schmidt operation to this. Now, what is the first stage of the Gram-Schmidt? It is orthogonalization. Now, if you notice that u1, u2, u3 are orthogonal. So, the first step of GS is orthogonalization, but we note that u1, u2, u3 are orthogonal or already orthogonal to each other. Why is it so? If you take the dot product of u 1 with u 2, you get 1 minus 1 plus 1 minus 1, which is 0. Similarly, dot product u 1 with u 3 is 0 and the dot product of u 2 with u 3 is 0. So, pairwise they are all orthogonal to each other. So, the Gram-Schmidt process will simply produce V 1 equal to u 1, V 2 equal to u 2, V 3 equal to u 3, because they are already orthogonal. So, the GS will give V 1 equal to u 1, V 2 equal to u 2, V 3 equal to u 3. Check, actually it is worth carrying out the Gram-Schmidt expressions explicitly and see that you get V 1 equal to u 1, V 2 equal to u 2, V 3 equal to u 3. So, the second step is the only thing that has to be done in this case, because they are already orthogonal. Second step involves dividing by the length of the vector. So, phi 1 is V 1 by length of V 1, phi 2 is V 2 by length of V 2 and phi 3 is V 3 by length of V 3. Now, the length of V 1 is length of V 1 squared is 4. So, the length of u 1 is 2, length of u 2 squared is 4. So, the length of u 2 is 2, length of u 3 squared is 2. So, the length of u 3 is 2. So, this is going to be equal to V 1 by 2, phi 2 is V 2 by 2, phi 3 is V 3 by root 2, and therefore, we get phi 1 as 1 by 2 into 1 1 1, phi 2 is 1 by 2 into V 2 is 1 minus 1 1 minus 1, and phi 3 is 1 by root 2, V 3 is 1 0 minus 1 0. So, we have got this OS, the OS required in this case is phi 1 phi 2. In this case, the Gram-Schmidt process was simple because the vectors were already orthogonal to each other. Let us look at another example. Let us take again R 4 and let us take the set S to be u 1, u 2, u 3, where u 1 is 1 1 1 1, u 2 is 1 1 1 0, u 3 is 1 1 0 0. Now, you see that these vectors are not orthogonal, and therefore, the Gram-Schmidt process will change them to produce V 1, V 2, V 3. Okay. Check that S is linearly independent. This is easy to check that S is linearly independent. You take alpha 1 u 1 plus alpha 2 u 2 plus alpha 3 u 3 equal to 0 vector and show all the coefficients must be 0. So, we will assume that this checking has been done. Since it is a linearly independent set, we can apply the Gram-Schmidt process. So, what is the step 1? In the step 1 is the orthogonalization process. We are going to look at V 1, V 2, V 3. We first are going to define V 1 as u 1, which is 1 1 1 1. In the calculation, we are going to use the norm. So, we will take the length of V 1 squared is 4. In the second, we will have to calculate V 2. To calculate the V 2, we start with u 2 and from that we subtract the V 1 information. The V 1 information in u 2 is given by u 2 comma V 1 into V 1 by norm V 1 square. Let us substitute u 2 was 1 minus 1 1 minus 1. You can recall that u 2 u 2 was 1 1 1 0. Let us substitute the correct values. U 2 was 1 1 0 minus u 2 comma V 1. This vector u 2 must be inner product with the V 1. We get 1 into 1 plus 1 into 1 plus 1 into 1 plus 0 into 1. So, that is 3. That divided by norm V 2 squared, which is 4, into V 1, which is 1 1 1. If you now simplify that, that is just 1 by 4, 1 by 4, 1 by 4 minus 3 by 4, or we can write it as 1 by 4 into 1, 1, 1 minus 3. So, that is my V 2, and since I would need the length calculations, I will write length of V 2 squared is 1 by 16, the component squared, it will be 12 by 16, which is 3 by 4. This 1 square plus 1 square plus 1 square plus 3 squared, that will give me a 12. There is a denominator square, which is 4 squared, 16. So, I will get 12 by 16, which is 3 by 4. The next one is to calculate V 3. How do we calculate V 3? From U 3, we must subtract V 1 information and also V 2 information, that is the projections basically. Now, let us say what is U 3 was 1 1 0 0, and the dot product of U 3 with V 1 is 1 into 1 plus 1 into 1, the remaining components of V 3 are 0. So, that is just 2 divided by the length of V 1 squared, which was 4, into V 1 minus U 3 V 2, V 2 is this vector and U 3 is 1 1. So, it will be 1 plus 1 2 by 4, because each component is there 1 by 4. So, it will be 2 by 4 divided by norm V 2 squared, which is 3 by 4 we have here, into V 2, which is 1 by 4 into 1 1 1 minus 3. So, which boils down to 1 1 0 0 minus half 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 and a half minus, there is a messy this thing, this becomes 1 by 6 into 1 1 minus 3. When we simplify this, we eventually can write this as 1 minus half minus 1 6, 1 minus half minus 1 6, and then minus half minus 1 6, and then minus half plus 2, minus half plus half, and that simplifies to 1 by 3 into 1 1 minus 2 0. So, that is what V 3 is. So, having got V 3, we will calculate norm V 3 squared, which is 1 plus 1 2 6 by 9, norm V 3 squared. So, now the process stops here, orthogonalization process, because we started with 3 vectors u 1, u 2 and u 3. So, we have to produce V 1, V 2 and V 3. So, we have produced V 1, we have produced V 2 and we have produced V 3. So, that the orthogonalization process, and the second step is the normalization process. In the normalization process, all we have to do is divide V 1 by its length, V 2 by its length, V 3 by its length. So, we define phi 1 as V 1 by norm V 1, phi 2 as V 2 by norm V 2 and phi 3 by V 3 by norm V 3. When we do that, we get phi 1 to be 1 by 2 into 1 1 1. We have all this information above. We have calculated V 1, we have calculated norm V 1, we have calculated V 2, norm V 2, V 3 and norm V 3. If we substitute all that, we get phi 2 to be 1 1 1 minus 3 and phi 3 to be 1 by root 6 into 1 1 minus 2 0. So, this is the Gram-Schmidt orthonormalization process with the given vectors. Then we will have L of phi 1 will be equal to L of u 1, L of phi 2, the space spanned by phi 1 and phi 2 will be the same as the space spanned by u 1 and u 2, and finally, L of phi 1, phi 2, phi 3 will be the same as the space spanned by u 1, u 2, u 3, and therefore, phi 1, phi 2, phi 3 is an orthonormal basis for L of S. So, thus given any linearly independent set, by using the Gram-Schmidt process we can extract an orthonormal basis for the subspace spanned by this given set of vectors. We will be using this repeatedly. Before we actually put this thing into action, we will now look at an important concept of orthogonal complement of a subspace, and then we will see how this Gram-Schmidt comes into the picture. Before that, let us make one small comment. What does this mean to us? This means to us that whenever you produce a linearly independent set, whenever you have a linearly independent set, you can always convert that into an orthonormal set producing the same space. So, what is the consequence of this? Let us immediately look at a consequence of this. Now, suppose I have R k and I have a linearly, I have a say even it is an orthonormal set, we not need, let us say we have an orthonormal set. Now, either S is a or basis, when does that happen? If S is phi 1, phi 2, phi r, this will happen when r equal to k. So, suppose I have an orthonormal set, if r equal to k, then automatically it is a basis because there are k vectors and they are linearly independent, because every orthonormal set is linearly independent, and therefore, since it is a basis and it is already orthonormal, it is an orthonormal basis for R k. So, given an orthonormal set, either it is a basis or it can be extended to a basis. Why is it that we can extend it to a basis? Because it is a linearly independent set, any orthonormal set is a linearly independent set, and any linearly independent set can be extended to a basis. So, it can be extended to a basis, let us call this as phi 1, phi 2, phi r. How can we extend it to a basis for R k? We can extend it to a basis for R k by appending enough number of vectors. How do you append? We already have R vectors, the dimension is k. So, we have to append k minus R vectors. Let us call them as psi 1, psi 2, psi k minus r, where psi 1, psi 2, psi k minus r belong to R k minus L s and linearly independent. So, we have extended the given orthonormal set to a basis for R k, but this basis may not be an orthonormal basis. What do we do next? We apply G s to B, the Gram-Schmidt. We can apply the Gram-Schmidt to B because B is linearly independent. We usually apply the Gram-Schmidt operation to a linearly independent set. Since B as a basis for R k is a linearly independent set, so we can apply the Gram-Schmidt operation to B. When we do the Gram-Schmidt operation, we go on doing orthogonalization and normalization, but the first R vectors are already orthogonal and normal. So, the Gram-Schmidt operation will do nothing to them, and it is the later stages it will come into action to orthogonalize and normalize the psi vectors. So, it will orthonormalize and will give us a OB which will retain this phi 1, phi 2, phi r because they are already orthonormal and now give us phi r plus 1 phi k such that LOB is the same as LB. That is what the Gram-Schmidt does, but LB is RK because B is a basis for RK and therefore, OB spans RK, it is orthonormal. Any orthonormal set which spans is an orthonormal basis. So, OB is an orthonormal basis for RK and you observe now that that is an extension of phi 1 phi 2 or it is an extension of S. The given the set we started with was this, we have now extended it by adding this. So, it is an extension of S. So, conclusion, any orthonormal set in RK is either a basis, in fact, or once it is a basis, it is an orthonormal basis, either an orthonormal basis or can be extended to an orthonormal basis. This is the question we raised earlier, that whether any orthonormal set can be extended to an orthonormal basis. We have answered that question in the affirmative now, that any orthonormal set can be extended to an orthonormal basis. We now introduce an important concept called orthogonal complement. And we will see how we use these ideas of extending an orthonormal set to an orthonormal basis. This idea of orthogonal complement is essentially to extend the Pythagorean geometry in 2 dimensions to this general setup of RK. So, we get many results analogous to the Pythagoras theorem. The Pythagoras theorem involves orthogonality and therefore, once we have this orthogonality concept, we can try to look at these Pythagorean properties. So, we have RK and let W be a subspace of RK. So, we have this big space RK and in that big space we have taken a subspace W. Now, what we do is we look at all those vectors which are this is the W, we look at all those vectors which are perpendicular to W. So, we denote that by W. So, let W perp denote the collection of all vectors in RK which are orthogonal to all the vectors in W. So, let us write this in a mathematical notation. So, W perp consists of all those vectors, the collection of all vectors in RK which are such that they must be orthogonal. So, x w must be equal to 0 for what? For all those w's which belong to W. So, it is the collection of all vectors which are orthogonal to those w which belong to W. So, this is called orthogonal complement of W. This is called the orthogonal complement of W. Now, first of all, is there any vector at all that is orthogonal to all the vectors in W, because we want to make sure there is something in W perp or not. Now, clearly the 0 vector is orthogonal to all the vectors, and hence in particular it is orthogonal to all the vectors in W, and hence it belongs to W perp. So, we observe the following. One, of course, W perp consists of vectors in R k. So, it is a subset of R k. Whenever you have a subset of R k, we wonder whether it is a subspace, and that is what we are going to investigate. So, is W perp a subspace of R k? Now, you may recall that in order to check whether something is a subspace, we must make sure it is non-empty, we must make sure it is closed under addition, we must make sure it is closed under scalar multiplication. So, first thing is theta k is orthogonal to all vectors in W in R k. Therefore, theta k is orthogonal to all vectors in W, because W is a part of R k. Therefore, theta k belongs to W perp, and therefore, W perp is non-empty. So, there is something in W perp, at least the 0 vector belongs to W perp. So, you have a non-empty set. Next, we have to check whether it is closed under addition. So, suppose x and y belong to W perp. What does that mean? X belongs to W perp means x is orthogonal to all the vectors in W, and y belongs to W perp means y is orthogonal to all the vectors in W. Therefore, x comma W is 0, the inner product of x with W is 0, and the inner product of y with W is equal to 0. Now, therefore, if I add two zeros, I get 0. So, x W plus y W is equal to 0, but the inner product is distributive. So, this is the same as x plus y W, because x plus y W is x comma W plus y comma W, and that is 0. This means x plus y is orthogonal to W, and therefore, x plus y belongs to W perp. Thus, W perp is closed under addition. It is closed under addition. We have to look at closure under scalar multiplication. X belongs to W perp, alpha is any scalar. Now, x belongs to W perp means x W equal to 0 for every W in W, and we are given alpha is R. Now, if I multiply 0 by alpha, I am going to get 0. So, alpha x W is equal to 0 for every W, but the inner product, the scalar constants or the numbers can be pulled and out of the inner product. So, it can be written as alpha x W is the same as alpha x W, and alpha x W is 0 from previous term. So, that says alpha x is orthogonal to for every W in W, and therefore, alpha x belongs to W perp. Therefore, W perp is closed under scalar multiplication. So, W perp from 1, 2, 3, what do we get? First one was non-empty, second one was closed under addition, third one was closed under scalar multiplication. So, W perp is a non-empty subset of R k, which is closed under addition and scalar multiplication. And therefore, W perp is also a subspace of R k. So, we have started with a subspace of R k, and we have constructed another subspace which is orthogonal subspace. All the vectors there are orthogonal to this. Let us look at geometrically a simple example of this. Let us take R 3, this is what we normally call as x y z axis. Let us say W is the x y plane. Okay. Now, what are the vectors which are perpendicular to all the vectors in W? Then we get the z axis. So, W perp is the z axis in this case.